Hello everyone, it's September 9th. Alright, let's get into it. Yeah, we still have one more to go with here because this is just the one way to do the KMP. I'm pretty sure the official solution has a different way to do KMP. So I have to do this again. And it has been almost official that I need to really pick up C++. Man, pick up C++. Just the thought of it is kind of bum me out. It's not something I want to do, but never mind, it's fine. Alright, insert greatest common divisors in linked list. Given the head of the linked list in which each node contains an integer value, between every pair of adjacent nodes, insert a new node with a value equal to the greatest common divisor. Greatest common divisor, we just go GCD it. Return linked list after insertion. So basically 18 and 6 we insert 6, 6 and 10 insert 2, 10 and 3 insert 1. Okay, so I need 2, right? I need 2, and while we have the second, we get a 2 value, and then this I can insert something in, then move forward. Yep, that's pretty much it. I don't think there's anything new to it. Just straightforward. Okay, so I need to use a private int GCD. Do you remember how to do GCD? If I think it's if b is larger than if b is larger than 1, then I return GCD a mod b and then b and return a. Something like this, right? Nope, I don't think so. Maybe we need to do this, swap it. So if a is bigger than b, then we have b and something smaller. If a is smaller than b, then we basically swap it. And eventually what happened is, let's say if it's a is 5, b is 2. Okay, a is 5, b is 2. Then basically 2 and 2, 3. 2, 3 will become 3, 2. Then become 2, 1. And then we'll return a. Huh, is it return a? Return the bigger one. That doesn't sound right. Okay, let's try another one. 4 and 2. 4, 2, one of them becomes 0. Ah, one of them becomes 0. So if it's larger than 0. Okay, let's double check. I don't remember. GCD. Return A. Yeah, I think this is right. If B is equal to 0, return A. Otherwise, GCD B and A mod B. Yep. Got it. Alright, so here we're gonna have we need to have a list node. We need a dummy. Uh, 0, next is head. Okay, and then what we're gonna do is list node P1 head, list node P2 head on next. While P2 is not equal to no, int G equal to GCD P1 dot val P2 dot val, and then we'll insert it. P1 dot next shall equal to new list node P1 dot next new list node G P1 dot next go to P2, right? And then P2 equals P2 dot next. No. P1 equal to P2. P2 equal to P2 dot next. Until we're done. Then we return dummy dot next. Q807. Just insert the GCD along the way. Okay, let's see if it's right. Great. Yep, looks good. What else can you try? I don't know, I think it looks good, right? Yeah, I'm gonna go for it. Yeah, it looks good. Simulation, we have the GCD, and then we just go through them. All right, that one is done. Okay, now we're gonna go for the second version of KMP. Okay, so we build a table. That is the LPS, the longest prefix suffix array. We have to resume the search in we don't need to start from we know what this is. As we search for the pattern in the text, if we encounter a mismatch, tell us how far back we will go in the pattern to continue the search, instead of starting the comparison from the beginning. We use the prefix table to skip over paths. Yeah, that's exactly what we're doing. Similarly, we construct the prefix table for the linked list By following the same principle, finding the longest prefix that is also suffix help us in efficiently finding where to resume the search if a mismatch occurs while traversing paths. We perform a DFS on tree, treating each node's value as part of the text where we want to match our pattern. As we traverse the tree, if a mismatch occurs, the prefix table tells us how much of the pattern we can skip based on what we've already matched. So I think what it's trying to do is, as we are going through, we will, as we're going through, right, as we're going through, we'll check. If something is not matching, then we will, just go back, right? We use the LPS, we go back and we'll try it again, and then we'll try it again until we cannot match. Like no matter what, we cannot match. Then we just skip. That's essentially what we do, right? We try it, and then we go, we try until j becomes 0, we cannot match, then we just skip this and then move on. Build a pattern, Yeah, I think it's doing along the way. It doesn't do after you hit the end. So we can try. We can try for sure. We will copy the entire thing. Okay, we'll still use this. We're not using this. Okay, so we're not using this. We basically will do DFS here. Second version of KMP, where we perform the match as we go through the DFS. In fact, this makes a lot of sense because the matching algorithm always goes through the source array one by one, the same as DFS. The benefit of this is that we can terminate early. That is, there is no need to, we cannot terminate early. The benefit of this is that we don't have to, have to go through the path a second time for the matching. Okay, this is all good, right? If not, return false, and then let's do DFS. We do need index, right? So this one, I think we need index. We have this path. We don't even need path. Do we need path? I don't think I need path. I need linked list and I need index. Right, I need index, okay? That's all I need. So this is not needed, but this is needed. Okay. All right. So if we go to an end, and okay, so we say if not node, return false, right? Otherwise, we don't do this. We'll do a comparison. We say if node val is equal to linked list index. If these two are equal, then we'll move on. Right? We'll move on. We'll return df self.dfs. We say node.left linked list index +1, or self.dfs node.right linked list index +1. Actually, we have to first check here if index is equal to len linked list, right? If it's equal to, then that means we have matched the whole thing, so return true. If it's not equal to, but then we have hit this, then that's false. Otherwise, if it's equal, then we move forward. If they're not equal, right, the two values are not equal, then what we need to do is, if index is larger than 0, then we will say return self.dfs. I mean, I don't have to. I can just do a while, because I will move. Okay, self.dfs. We say node. I don't move the node. Linked list is still there. The index is going to be LPS. Oh, I forgot the LPS. Right. Oof. Then linked list index shall be LPS index -1 LPS, right? Because this current one doesn't work, so I go for the previous. Hold on. All right, I'm back. Where are we? Yes, we say if it doesn't match and index is larger than 0, then we try it again. And we have to do index -1 to go LPS to find, at that point, what's the length. So, and this will become the index for the next matching, right? Otherwise, index is equal to 0, then we will return, actually, we return this, right? We return self.dfs, node.next, node.left, linked list, index, LPS. Or basically just skip it because it's not possible. Or self.dfs, node.write, linked list, index, LPS. Then we're going to delete all of the rest. Huh. What? What is this? What is this bonkers? Oh, this can be optional. Okay. Right? We're following that. We say if that's the case, then we return true, and then when I return true, we'll short circuit it. And then if it's not, then we have reached the end of the path and it's always false. And if they're the same, then we have a match, then we keep matching, right? We keep matching. This is what we keep matching. We go left or right to the next node and then index +1, right? And if it's not a match, then we use LPS to find where's the next possible match. And if index is equal to 0, then, I might be able to, no, because if it's not a match, I have to rematch the node with something else, right? I will rematch the node with something else. And we keep matching until index becomes 0, right? If index becomes 0, then we just move on. Right, we just move on. All right, let's see if this one is right. LPS has not been defined. Did we not do LPS? Oh, I did linked list. All right, first things first. I don't know, this one should be here, right? And then we'll do LPS. So LPS self.get LPS. Wait, what do I have here? Just array. Just array. That's it. Just array. So linked list. Okay. Let's see if this one works. I mean, it should be, I think slightly faster at least. We don't have to redo the whole matching part. All right, let's run it. Okay, this is easy to solve. Try it again. Okay, so far so good. We have a wrong answer last time. Let's try this. Oh, not bad, not bad. All right, let's try it. I think it should be faster. Very, very fast. I mean, in fact, you see this one is faster even than the Java version, because the Java version is not KMP, and it's all m times n. So understandable. And this is KMP, but we did a lot of, I would say, unnecessary, because in this algorithm we produce the path, the full path, which means even if we had a matching early on, we still produce the full path and then do the matching. So there are a lot of unnecessary work here. This is the ultimate solution where we will, as long as we find a match, then we just turn it off. And in fact, the implementation is not that complicated. Of course, you have to do the LPS, which I think is the most important, most difficult part. I don't know how to do this. Like if you ask me to do KMP from scratch, I know the general idea, but LPS is always something I can, and you cannot memorize this. It's a complicated piece of algorithm. But you understand it, and hopefully, it's always a hope that you can do it from scratch. And in fact, if you know how to do this, the LPS, the matching part is not that bad, because the two are has similarity. I mean, the most difficult part I think is this, to realize this line. This line is the most difficult part. To know that when there's no matching, because you set up a current length, right? When there's no matching, you have to reset the current length and then try to match again, right? Reset the current length and try to match again. I mean, the current length is used as kind of, you can call it J, right? It's the prefix. It's the, what's the next index in the prefix for you to match, and you just need to reset it. Yeah, this is the tough part, but it was good. This is it. This is the I won't say the right, because technically there's no right or wrong, but this is what we hope that LPS can give us, KMP can give us. Okay, that's good. Very happy that we got this one done. I think we can add this to a good interview question, because it has two solutions, right? It has the naive solution that people can do, and it also examines a candidate's understanding of both linked list and tree traversal. All very basic, right? Very basic tree traversal, very basic linked list, but we have to put these two together, and you have to do subarray matching, and then you can do the the brute force to do the subarray matching, and then during the interview you can try to prod along, see if the candidate understand, if they have heard of KMP. If they have not, that's actually I think I want to do interview in the future, and the way I'm going to do it will be different. Of course, the question I choose will always be, you can solve it with brute force or some very straightforward way. Might not be the most optimal, but yeah, you can do that. And then you ask if there is any optimal, a better way that you can think of, and the candidate can do some thinking, brainstorming, and see if they can find a better way. And if they cannot, then I will try to prod along and see if they can. I don't know, man. This is actually hard. Yeah, this is actually hard. I was just trying to think maybe we can give some hint. Like if you want to do KMP, give some hint. Maybe we can create this array. You know what? No, I think it's good. Right? I explain what the idea behind the KMP is, and the key is we need to produce this longest prefix suffix array, and we explain what it is and have the candidate implement it. Can you implement the KMP? can implement LPS. I don't know, you can twist this problem a little bit. Yeah, you can twist the problem a little bit. You know what? You can even just go ahead, substring matching. Give me an algorithm of substring matching, right? And then if they have heard of KMP, yeah, if they have heard of KMP, I doubt they, it doesn't matter. If they have heard of it, even if they memorize it, that's okay. But I need them to explain it to me. Yeah, straightforward like that. And they will not be judged by whether they can come up with KMP or not, but they will be judged by whether they can implement it after I gave them an explanation. Yeah, that's kind of, I don't know how the company really wanted the interview, but this is how I would do it. All right, that will be it. I'll see you guys tomorrow. Adios.